Good evening, everyone. Welcome to the McDonald Observatory live stream. My name is Saul Rivera. I'm the online program specialist here, or coordinator here at the McDonald Observatory. And today I'm joined by my awesome colleagues, friends, and guests as well. And so happy that y'all can join us today. And before getting more into it, if it's your first time joining in on the stream, welcome. If it's your second, third, 10th, 20th, 60th, 70th, nth time joining, also welcome. And just want to go around the room and have everyone introduce themselves. Um, Ryan, introduce yourself.
Howdy guys, my name is Ryan and I'm one of our program specialists here at the Visitor Center. So I do a wide range of programs like daytime stuff, tours, solars, but I help out with the star parties and I help out with the live streams like what I'm doing right now. So I am in one of our domes here at the Visitor Center that houses our robotic telescope, and I'll be operating it as the telescope operator. So all of the live images you're going to see are going to be coming from me. They will be in black and white though, because that is our best camera. But we have a slew of targets we'll be offering today.
Thank you, Ryan. And Jay, give us a bit of info about yourself.
Yeah, so my name is Jaye Smittick. I'm the K-12 education coordinator at McDonald Observatory. So I get to do a lot of the wonderful things that Saul and Ryan get to do. And then I also get to host field trips at our observatory, teacher workshops, and also go out and get to talk to students at their schools too. So it's really awesome.
Thank you. And for our awesome guest today, Zoe. Zoe, tell us a little bit about yourself.
Yeah, hey y'all. My name is Zoe Hackshaw. I'm currently a PhD student at UT Austin. So, unlike our other friends here on the live stream, I'm all the way in Austin, Texas, very far from the observatory. But I'm excited to share with you guys a little bit about what I do and what it looks like to be an astronomer.
Thank you, Zoe. And thank you as well, Ryan Jay, for joining in tonight. For those of you all joining in the live stream, thank you again for joining in tonight. So we do have moderators in the chat to answer any questions you have, both on Facebook, YouTube, and Instagram. So do feel free to drop those questions in the chat. They will be answering those along. If there's any question that might be require more detail or just be awesome to answer on stream, they'll pass that along for us to answer. If you by chance can't stay for the entire stream or miss the stream, this will remain on our YouTube channel, just McDonald Observatory on YouTube with all the other streams we have done. We've done over 70 streams. This might be our 78th stream at this point, so we have lots of variety of them. And yeah, hopefully you can join in on this awesome stream. Today we'll be talking about compact objects. So a compact object in space just means something that's very dense. So this means white dwarf stars, neutron stars, and black holes. So if you want to learn more about these things, how they form, more of their properties and stuff, you've come to the right place. But before we get more into that, I kind of wanted Zoe to talk a bit more about herself and what got her into astronomy.
Yeah, I would love to. So as I said before, hey, my name's Zoe. I'm an astronomer, which I told y'all. I am a PhD student at UT Austin, and I obtained my bachelor's in science in astrophysics from the University of Florida. Go Gators. And I first got into astronomy because when I was younger, my dad and I went on a trip to the Kennedy Space Center, and I just absolutely fell in love. I thought that space was the coolest, as I'm sure a lot of you do. But also another reason why I got into astrophysics specifically is because I failed my AP physics exam in high school. And I share that specifically because nobody's a perfect scientist, and you don't have to be amazing at geometry or calculus or even physics to be successful as a scientist. So you are a scientist just for showing up today on the stream and being interested in space. So that's kind of generally what got me into space. But specifically, I'm a galactic archaeologist. So I use stellar spectroscopy, or the light that we get from stars. And I use stars in our Milky Way kind of as fossils to really understand how the Milky Way formed. This picture right here on the right is one that I took at the 2.7 meter telescope at McDonald Observatory. And that's kind of the Hobby Eberly telescope, as you can kind of see right there on the hill. And this is one of my favorite pictures to kind of show and talk about, because although, as you can imagine, that night you can see the clouds at astronomy, specifically ground-based astronomy, don't really get along super well. But you can see that gorgeous rainbow over kind of the Hobby Eberly telescope. And I thought it was very poignant, because really all that I do is study rainbows. I study the light that we get from stars. I study rainbows for a living. And that's essentially what I want to do for the rest of my life. So a little bit later, y'all will get to hear about how I study rainbows, especially in relation to black holes.
Thank you. Yeah, rainbows are really cool, and kind of one doesn't think rainbows and black holes going together, but they really do. As Zoe mentioned, the work she does here is here at the McDonald Observatory, and the McDonald Observatory is in far west Texas. Very far west Texas. We're basically in the middle of nowhere. We're about 500 miles away from Austin, from main campus, but we're still considered to be part of UT campus, UT Austin itself. And being in the middle of nowhere has its advantages, such as giving us very nice dark skies where we can do research. So giving us these nice dark skies, we can see the Milky Way, and being able to see the Milky Way lets us see all the stars in it, and also, as you can imagine, the dead stars in it, so we can see what gets left behind when these stars die. Now, for tonight, to be able to see these stars, we're not going to be using these giant research telescopes, the ones Zoe uses, but we'll be using some smaller ones, some located at our visitor center. So at our visitor center, we are open to the public, usually Tuesday through Saturday throughout the year. And during Tuesday, Friday, and Saturday nights, we do public star party programs. During these programs, we have telescopes set up behind the visitor center, and one of the telescopes is inside these domes used for the programs. That's actually where Ryan's located right now. He's inside the dome where the arrow's located at, and we usually have an eyepiece on the telescope, but for tonight, we have a camera attached to that telescope. That camera is then connected to one of our computers, and the computer is connected to to y'all, to the internet, so y'all can see what the telescope is seeing. If you want to get some more details about the telescope and the camera we're using, that's in the description of this video, so y'all can get more ideas about what's going on software-wise and telescope-wise. And for those of y'all more on the tech-inclined side. Now, to get a bit more idea of kind of what's going on, or better yet, of like star formation wise, we're going to pass it over to Jay to get an idea of what's going on with the stars. Because to get more idea of what happens when the star dies, we gotta know more about how the star was born. Off to you, Jay.
Thank you. So yes, so when we talk about stars' lives, we're going to break it down into different sizes. And so specifically, we're going to focus on basically how low mass stars and high mass stars live their lives. But there are really small stars that we don't really talk about because they don't really go through other stages. So I'm going to talk about low mass stars. I'm going to go with this. There we go. Okay, so for a low mass star, they're going to be born in what are called stellar nurseries. And these stellar nurseries are beautiful. And they call them nurseries because they are filled with little baby stars, even though you wouldn't want to hold these baby stars because they would kill you. But they are still really gorgeous and wonderful to look at because a lot of times they are really big, bright, and hot stars. But like I said, we're going to talk about low mass stars, which are going to be stars like our sun. So stars like our sun are born in these stellar nurseries because they're filled with hydrogen gas. So this hydrogen gas clumps together, and eventually we increase in pressure, and we're able to have nuclear fusion. So whenever an object starts to have nuclear fusion in its core, that's when we have a star. So an object can't be a star unless there is nuclear fusion taking place. And this nuclear fusion is literally squeezing and fusing hydrogen atoms and creating helium atoms. And so the more hydrogen fuel the star has, the longer it will live. So right now, our star has burned through about half of its hydrogen fuel. It's about 4.5 billion years old, and it still has about half of its fuel left to live. So over time, the star is going to fuse its hydrogen fuel, and it's going to run out of it. And at the end of this, it will be filled with helium. And helium is a much larger and heavier element. So whenever the star has converted all its hydrogen to helium, it's actually going to start to swell up. And it's kind of like it's inflating too. So it's going to become something called a red giant star. And this will happen to our sun in about 5 billion years. And so whenever it swells up, it will actually, as you can see in this animation, engulf most of the inner planets. It won't engulf Earth, but it will reach to about Earth. So it will be pretty much right next to us, which means that we'll have a really hot star right next to us. So even though we won't be swallowed up by the sun, we are going to be completely burned up by the sun. But we probably won't even be here on Earth anyways by that point. So once the star has swelled up and kind of reached this limit, because now it is fusing that helium into heavier elements, it's going to do that a lot faster because it doesn't have enough heat to do this process for a long time. So it will swell up, become a red giant. And then whenever I think of this next part, it's going to sound a little silly, but just bear with me. I kind of think of the red giant phase as someone who's eaten way too much food, like maybe someone at Thanksgiving. And so you have a really full belly. And so the easiest and quickest way is to kind of just, it's a burp. So that's what our star is going to do. It's going to swell up, get really, really full and kind of reach this limit. And so the core of the star is still trying to push out all this energy, but basically the shell of the star is not going to be able to contain it. So it's going to actually keep pushing off this energy, and it's going to start burping. So that burping motion. So it's going supernova like a lot of people assume our star will do. Our star isn't massive enough to do that. Hello. But it will start to push off these extra layers, kind of a slow process. And so all these extra layers are going to become a nice, pretty cloud around the leftover core of the star. And the core of the star is going to be really, really hot and really, really dense, going back to our compact objects. So this leftover core of the star is called a white dwarf. And that cloud that is created by that burping action is called a planetary nebula. Now, don't let the name deceive you. Planetary nebula has nothing to do with planets. So they have this name because older astronomers, whenever they first started studying these objects, they actually thought they were planets or something related to planets. And then we found out that they weren't. But if you read anything on ancient astronomy, you'll learn that astronomers are really, really lazy. And so, no offense, Zoe, but we don't like changing names of things, especially if it's been around for a long time. So they're called planetary nebulas, but have nothing to do with planets. But they're really, really beautiful. But the main thing is that white dwarf star that I mentioned. So that is the leftover core of the star, but it's also really, really, really dense. So that leftover core would be about the size of the Earth. So kind of think of it, we have all of the sun, all of that mass and everything condensed down into the size of the Earth. And just to give you a little context, the sun makes up 99% of the mass of the solar system. So that's a lot that we're putting down, shrinking down. Another cool way to think of it is just how dense these white dwarf stars are. If we were to take just a sugar cube amount, just like a little sugar cube amount of material from this white dwarf star, that little sugar cube would weigh about as much as an 18-wheeler. That's how dense this material is. And so being really dense and compact also means that these objects are extremely hot. So the current surface temperature of our sun gets about to 10,000 degrees Fahrenheit. These white dwarf stars will be about 100,000 to 200,000 degrees Fahrenheit. So extremely hot. And so after these white dwarf stars have basically kind of lived out their lives, we're going to kind of wonder what happens next. But before we jump to that, let's see if we can look at one of these beautiful planetary nebula.
Yeah, and we actually do have one ready. So we're actually going to pull up the view of that one, It's a really cool one called NGC 7662, but has a much funner name, which is called the Blue Snowball, which is very fitting for Christmas time. Now, for this one, looks kind of very nice and bright and white right now. As Ryan mentioned, we're using the black and white camera. But if we mess with the slider a little bit, you can see there seems to be like layers in it. And actually, Ryan, if we can we also zoom in a little bit on the image? Ooh, there we go. We're
I
zooming
got
in.
you covered.
Ooh, thank you. Ooh, there it goes. You can see
So-
there's actually like little rings in there as well. As Jay was mentioning, kind of like as kind of like the star was kind of like burping as it was dying. Dale's kept on pushing layers, and actually, we can see the white dwarf in there. We can see the little white dot in there. Ooh, I actually did not think we were gonna be able to see that. So that's actually a really fun surprise tonight. So you can see we can see the layers in that one. This planetary nebula is getting to about so actually the pinpointing of the distance of these planetary nebulae gets a little bit difficult. So the range of the distance is anywhere from 1800 to 6400 light years away. So we got a good kind of range of distances. Part of the reason for that is you can think of these nebulae kind of being almost like a cloud of fog. You can see the cloud, but the actual exact edge of the cloud gets kind of difficult. Same thing is going on here. So we know the cloud is there, but the exact edge, it's kind of difficult. Some of the more modern estimates put closer about 2,500 light years away, but there's still some debate, some of the more exact distances. But either way, this cloud is getting to trillions of light years in diameter. And even though the exact size is being debated, we can measure its expansion rates, how fast the cloud is growing, which is expanding at about a speed of 130,000 miles per hour. So it's growing pretty quickly. As Jay mentioned, the core of the white dwarf star can get extremely hot. The estimated core of this specific white dwarf star, the one you can actually see there, which I'm still really happy that we can actually see the white dwarf at the center of this blue snowball, is estimated to be from 140,000 degrees Fahrenheit to about 200,000 degrees Fahrenheit. So still very, very energetic. And to actually get the blue snowball aspect of this, going to show a picture taken from NASA so we can actually see the nice blue color of it. So let me bring that up and see, we got a nice blue color of it, giving us more of the blue snowball. So when you actually see the blue snowball aspect, like through a telescope, so you're seeing it with the eyepiece, you can actually get a blue color just through the telescope. And actually, when I'm showing people that view through a telescope, I'd say the snow is kind of radioactive because it almost gets like a blue-green color.
Mhm.
And the blue color we're getting is actually from the oxygen in the cloud. Since that leftover core, the white dwarf star, is lighting up, energizing all the leftover gas, the gas being energized is the color we get is from the type of gas left over. So you might get like pink for hydrogen, kind of like in Jay's background with the Orion Nebula. You might get like yellow helium, red carbon, blue oxygen, so on and so forth. Another cool thing about the blue snowball, we believe the star that created this when it died was actually getting to about the size of the sun. So there's some really cool things. So not only is it thematic for being, the holidays, but also it was about the size of our sun. But now that begs the other question. What happens when an even more massive star dies?
Saul, can I tell you a super fun fact about white dwarfs really quickly?
Ooh, yes, please.
So we have heard of exoplanets, right? Exoplanets are planets around other stars, so planets not in the solar system. And we can kind of tell what's inside of the planets, like inside of Earth, using things like seismology, but it's really, really hard to tell what's inside exoplanets. And actually, some work that's being pioneered right now at the Hobby Eberly Telescope at McDonald Observatory by a fellow scientist named Malia Cao has actually been using white dwarfs to look at the inside of planets. And that might sound really weird for a second, but you can imagine, as we said that for example, the sun's going to kind of swell up and kind of eat some planets. And you can imagine that would cause some of the planets on their orbits to be unstable. So maybe when that orbit is unstable, that planet will eventually spiral in and then get torn apart by the forces of the white dwarf. And then all of kind of the material and everything that exists within the planet will just be kind of slapped onto the surface of the white dwarf. So by looking at white dwarfs that have eaten planets, you can tell what the inside of planets are made out of. And that's ongoing research being done at McDonald Observatory right now.
Oh, that's so cool. Ooh, that's so cool. I'm geeking out as well because I'm learning as well. This is cool. Ooh. Just planet destruction. It sounds like cataclysmic to other people, but for like astronomy nerds, like, ooh, learn more about this. And now, with the stars and dying and such, which is also cataclysmic and sounds world-ending. But now the question is, what happens next when an even more massive star dies? So beginning stage is basically the same. Fusion at the core, starts getting larger and larger, becoming a red giant. But with the more massive star, you're getting heavier and heavier things being fused at the core. You can get into heavier elements being fused at the core. Now with heavier elements being fused at the core, you can get an even larger star. Now, stars are going through a process called hydrostatic equilibrium. That's actually the favorite word of one of our past colleagues. In hydrostatic equilibrium, there's basically a tug of war going on. Gravity's want to push everything inwards, and the nuclear fusion of the at the core wanting to push everything outwards. That internal pressure. Now, with the heavier elements being fused inside, it's causing the star to get really big. Now, there is actually a really big star that can be seen in the night sky, actually this time of year, during the winter, the star of Betelgeuse. And this diagram is actually Betelgeuse if it was placed in our solar system, replacing the sun. As you can see, Jupiter would be the closest planet to the center. Betelgeuse is huge and is in the constellation of Orion. Don't say name 3 times, bad things may happen. I've only said it twice, so we're safe for now. And I have a good gap right now. So if I say it again, we're safe. In our case, this is a super red giant that's going to go through something really soon, which is what happens with these super massive stars. When they die, they don't push away their outer layers little by little. When instead happens, during that kind of end stages, there's a tug of war going on. Things going in and out, heavier fusion going on in at the core. It's going with that huge tug of war, and it goes all the way in. There's so much fusion at the core, so much energy being produced that sends everything going flying out in one huge burst and becomes what we know as a supernova. This huge burst of energy that gets sent flying out all in one go. So that big star in Orion, Betelgeuse, when it finally goes supernova, which can happen literally any second, or the next 100,000 years, we got good leeway going, or might have already happened, we just haven't seen light from the explosion yet. Some think when that does happen, it could be so bright it might even rival the full moon. That's some of the estimates some people have. So I'm on team Betelgeuse blowing up, so hopefully that happens soon. But that's not the only time we've seen supernovae happen. They've actually happened even more recently. So actually one of the targets we're going to be seeing next is a supernova remnant. What got left behind when a star, actually about 8.5 times more massive than our sun, blew up, because a star has to be about 8.5 times more massive than our sun for it to go supernova. Are we ready for the next target, Ryan?
We are ready.
Ooh, nice. So for our next target is called Messier 1, also known as the Crab Nebula. Here we are. So this kind of nice kind of like web of clouds and such, almost like a little network going on, is this one, Messier 1, the Crab Nebula. So this is a supernova remnant. This cloud is about 6,500 light years away, getting to about 11 light years across, and may not seem like that much is going on, but it's actually expanding at a rate of about 3.5 million miles per hour. So since we started the program and by the time it ends, it will have already grown about 3.5 million miles. Another really cool thing about it, as I mentioned, when Betelgeuse blows up, it will be extremely bright, be able to be seen during the daytime and all over. When the Crab Nebula blew up, similar things happened. When it actually blew up, it was so visible that it was visible during the day for about 2 weeks. It was visible to the naked eye for about 2 years. You could just go up into the sky and see it with the naked eye. It blew up July 4th at 10:54, and to many people was known as a guest star, like Zoe. Zoe's our guest star for tonight. And the Crab Nebula wasn't the only type of guest star throughout history. There have been many reports of guest stars happening throughout just all of human civilization. There have actually been cave paintings of people just jelling down the constellations and there being a random extra star. Turns out the extra star was just a supernova that appeared. We haven't really had a supernova in our galaxy for a while now, actually since Messier 1. Supernovae happen in galaxies about every 1 to 100 years. So hey, we might end up having a bunch of supernovae happening at once. It might be really cool or very scary depending on how they play out. But might be overdue for one. But this is a really cool one, the Crab Nebula. If you're wondering why it's called the Crab Nebula, in the 1800s, one of the lords drew the Crab Nebula and he thought it looked like a crab. So that's why it got the nickname. We sometimes get asked why they get the names, and people are like, it looked like a crab. So that's why it got the name. At least the drawing looked like a crab. Looking at it like this, doesn't really look that way. But if you want a bit more colorful view of it, or kind of like the more famous view of it, you might recognize more of the NASA picture of it, which is this view of it. All of the greens and yellows and such. And actually during the supernova explosion, it's kind of when you can get some heavier elements being made. The materials moving so quickly is where you get things like gold and calcium. So you might have heard the phrase that we're made of star stuff. So that's like literal, the calcium in your bones was made in supernova explosions. So that's like a superpower thing. Like you can just say like, hey, my bones are made from dying stars, dead stars. Or if you're gifting someone something made of gold, you can just be extra fancy, say, this was made in the heart of a dying star. And you're technically scientifically accurate. But we were talking about things left over from when the star dies, not the compact thing, not the things sent flying out. So there's something left over inside the Crab Nebula. Oh, also before I forget, where this was located. It's located above Orion, so, it's near Betelgeuse, in the constellation of Taurus. So this is where people were seeing a random star for a little while. And kind of to see where we're going next, it is this one, neutron stars. So a neutron star was left behind when a star goes supernova. These are extremely dense, even denser than white dwarf stars. These are what gets left behind, as I said, when a supernova goes off. These are about the size of a city. They can get about the size of, we can say they're getting to about the size of New York City, per se. As Jay mentioned, a little spoonful of a white dwarf star can weigh about as much as an 18-wheeler. A little spoonful of a neutron star can get to about as much as a Mount Everest. They're extremely dense. That's assuming you can even get close enough to a neutron star and not get vaporized immediately from how energetic they are. Because they're really energetic. The magnetic fields of a newly formed neutron star can get to millions, billions, some say can get quadrillions of times more powerful than that of our planet Earth. They're crazy strong. Basically, it's like a giant atomic nuclei. As you're going into like the layers of a neutron star, basically the layers of us the parts in there are like the nuclei and stuff are being nicknamed after pasta. Like they're like literally like there's a gnocchi layer and like the spaghetti layer and like the lasagna layer. It's become like nuclear pasta. That's literally like how dense it's getting inside. It's breaking like the laws we know of just from how dense it is at the core. They're crazy powerful and crazy dense. And they spin super, super fast. The neutron star at the center of the Crab Nebula, known as the Crab Pulsar, spins about 30 times per second. And it's just lighting up that giant cloud of gas. But you might be wondering, what happens when the even more massive star dies? It's starting to sound like a broken record player. So what happens when a star is about 30 times more massive than the sun? You got that kind of tug of war going. And out, and out, and out. But in this case, it starts falling in and keeps on going and going and going and just collapses on itself, creating the thing that everyone finds super, super cool in astronomy, a black hole. Now, black holes are really, really cool, and let's start trying to learn more about them. And usually when you think of a black hole, you think of them being inside a galaxy, like the center of a Milky Way or even more distant galaxies, like our next target, NGC 891, known as, and I have to slow down for this one because it's a tongue twister, the Silver Sliver Galaxy. And I see we do have it in view. There we go. It's a very, very pretty galaxy. It's a nice edge-on, unbarred spiral galaxy. It's getting to about 30 million light years away in the constellation of Andromeda. It's about 130,700 light years across. Actually, with how pretty it looks like, it's actually a first for lots of telescopes. There's been several observatories when they first opened light, at least recent observatories, that they end up using this galaxy as the first thing they pointed at, just to see if their telescope's working. And actually, a lot of people believes if we could see the Milky Way from far away, that this is how the galaxy would look like, how our Milky Way would look like. It's actually quite a pretty galaxy. Except for the tongue twister name. Even typing it out earlier today, I accidentally typed it up as Silver Galaxy. And so if only the names were a bit easier, though. Also, astronomers gotta have fun with naming things every now and then. But as I was saying, when we think of black holes, we think of them being these gargantuan things only at the center of galaxies. Material being fed into them. But galaxies or buried black holes can be much smaller. And there's even one that can be seen in our own night sky. So we go outside and look towards actually these can be seen during the summer, even during the early night of the winter, in the constellation of Cygnus, the swan. If you're looking towards his neck area, or if you're looking at the Northern Cross part, where there's a little bubble in this image provided by astronomy.com, you can see as we're zooming in, there's a little area marked as Cygnus X1. there's a black hole located there. But we can't see it. But how do we know there's a black hole there if we can't see it? And that's where Zoe comes in. Do you want to tell us, Zoe, how we can detect black holes if we can't even see the black holes?
I would love to tell y'all about how we can detect some black holes. So black holes, they kind of come in a couple of different varieties. And one way that we can see black holes is if they're eating other stuff. And just to go over why it would be so hard to see a black hole in the first place is because these things are so dense that not even light can escape it. So if there's no light coming from it, how the heck do we even see where the black holes are, what a black hole looks like? And one example is if, like I said, a black hole is eating a bunch of stuff around it. So if a black hole is accreting a lot of things, or it's just eating a lot of material, we can see them kind of easily. And that's because as all of this material from maybe a neighbor or a dying star or something is being pulled into that black hole, you're really heating up this material and you're causing this material to glow in the infrared part of the electromagnetic spectrum. This is the first ever and only ever image taken of a black hole. So this isn't some like NASA generated, like computer generated artist rendition. This is an actual picture of an actual black hole. This was done by the team at the Event Horizon Telescope. This took years and years and years of work just to produce this one tiny image. But here you can see that black hole, the silhouette, and kind of the accretion or what that black hole is eating around it. Now, I say that you can see it pretty easily because, like I said, this took teams from over 80 institutions all over the world to make this one picture, which is why it's important that science is really kind of a global endeavor. Like we all have to work together to understand the cosmos around us. But what happens if a black hole isn't eating anything? What if it's dormant? If it's dormant, it means that it's not kind of accreting anything. It's just a black hole sitting in space. So it's not eating anything. It's not heating up any material. But there is one trick that we can use to actually look for black holes. And that comes in with binaries. Now, y'all might have heard of binary systems before, like maybe the two stars on Tatooine, that iconic sunset. And we can actually use binaries in kind of a cool way to try to detect black holes. Now, we know that in a binary, these two stars kind of orbit the center of mass of the system, or it just looks like one star is orbiting another star. But what if I told you a couple of different times we've seen a star moving like it's orbiting something? We can see how a star is actually moving in the sky. But when we actually go to see what the star is orbiting, there's actually nothing there. There's no light coming from that companion anywhere on the electromagnetic spectrum, not in the UV, not in the infrared, in the radio, absolutely nothing. And it turns out that we can use a little trick looking at how that companion star, how the star that we can see is actually moving to estimate the mass of the dark thing that it's orbiting. And we can actually tell that this is a star orbiting a black hole. Now, this has happened 3 times so far with Gaia. Gaia is a mission run through the ESA, the European Space Agency. And actually, a fun fact that I just learned is if any of y'all have that Lego set of the Milky Way and you're building it, the telescope that's featured in the Lego set of the Milky Way is actually Gaia, which I love. I think that Gaia has completely revolutionized what we know about the Milky Way. It's amazing. I could nerd out about Gaia forever. But this is what Gaia looks like. It's located in space, and it actually works by, as we can see, it scans the sky multiple times a year. In doing so, it tracks how stars are moving. And when you know how stars are moving, you can kind of get the velocities of stars, and you can see if these stars are moving and orbiting something like a black hole. So like I said, 3 times this has happened in Gaia. We've seen that a star is orbiting something really huge, and we know that it's huge because of the velocity of the star, but we have no idea. We can't see any light coming from anywhere, so we know that it must be a black hole that the star is orbiting. Now, one specific one of these systems that I want to talk to you about today, which is what has consumed my life for the past year, is Gaia BH3. It's a black hole and star pair. So this is a binary system in which the black hole at the center of the system is 33 times the mass of our sun. And the star, the thing that we can actually see of this system, is about 0.8 times the mass of our sun. So why is this system weird? Why did I spend so much time of my life dedicated to this one particular system? Well, as we can see, this is actually one of, let's see, an elusive type of black hole called an intermediate mass black hole. So kind of like Saul mentioned before, this we have a couple of different camps of black holes, right? The first is stellar mass black holes. And that's what we were talking about before, stars kind of living and dying and creating a black hole. And then there are also black holes at the center of galaxies, and these are called supermassive black holes. Not just a song by Muse, it's an actual real thing. And those are kind of 1,000 times the mass of our sun. But in between the like tens to thousands range, there's this weird gap called an intermediate mass black hole. And it's really, really, really hard to find these kinds of black holes. So this is one of the reasons why this system is cool. This is also the lowest metallicity star to be found orbiting a black hole. And by that, we're going to have a quick aside about metallicity. So astronomers are annoying, and much to the chagrin of many chemists, we call any element that's heavier than hydrogen or helium a metal. So anything carbon, calcium, argon, astronomers just all call them metals. And that's because, as Jay kind of mentioned, at the beginning of the universe, there's hydrogen and helium and trace amounts of lithium, but all of the rest of the elements are created either through the life or deaths of stars. And so astronomers quantify all of the rest of these metals just by calling them metals. And this is the lowest metallicity star to be found orbiting a black hole. So this star has the tiniest amount of metals that we can see, which also means that this is one of the oldest stars that we found to be orbiting a black hole, which could be cool and tell us a little bit about like black hole formation history and how black holes kind of form over time. And kind of most importantly, we don't really know how a system like this forms or really survives. And it's kind of this question that I wanted to highlight and what inspired my work on this system. So when we're talking about how this system formed, there are two general pathways that this weird black hole star system could have formed. And one is maybe they were born this way. So maybe these two stars were born together and just like a regular binary system born together, and one star is orbiting the more massive one, and then the massive one goes supernova. And then doing so, that would create a black hole at the center. And then you would see just that regular star orbiting that black hole today. But kind of the other option for how these stars formed, and yes, these two titles are based on pop icon songs, but the kind of other way that this could have formed is through something called dynamical capture, where these two objects kind of found their way together. And essentially how that would work is you have just a regular black hole. It's not near anything else. It's not really interacting with anything else, but maybe a star kind of just got a little too close to it. So a regular unassociated star got a little too close to it and then became bound to it, got kind of trapped in its gravity. And so what we kind of wanted to ask was, how can we use observations? How could we use our science to try to understand how this system formed? And one of the questions, kind of the more specific question that I wanted to ask, is what can the chemistry tell us? So stars born together should look the same. If we know that stars are born in these stellar nurseries, and if stars are born together from the same stellar nursery, then those stars should look very chemically similar. So maybe in the born this way camp, if you have one star, but maybe a star close to it went supernova, you can imagine that when that star went supernova, it kind of dumped a lot of material onto its companion. And this would change the chemistry of that star relative to its neighbors. So our Gaia BH3, this particular star, would look different compared to its neighbors because of the extra material that it got from the supernova. Whereas in kind of this other dynamical capture, we belong together camp, this star would look exactly like its neighbors because these stars were born together and it was just a regular old star that just happened to get too close to this black hole. And the way to kind of visualize this and what I ended up doing was going out to McDonald Observatory and getting almost 45 hours of observations on this star. And this is kind of a time lapse of what it looks like of me opening the dome. So this is me starting up the telescope for the night. That big telescope you'll kind of see it move in a second. It's our 2.7 meter telescope, our Carl and Jaye Smittick telescope at McDonald Observatory. And I'd like to start with this because a lot of folks may think that astronomers like look through an eyepiece all night. And while that might be cool, what kind of actually happens is that the light enters the telescope and then gets sent down to a different room to our spectrograph, and then it comes right back to our computer. So this is what that image looks like. When I look at a star, this is what I'm actually looking at, is the computer in the control room, and this is the spectrum of a star, so kind of the rainbow of a star. And what we're looking for are these little absorption features. So this is a two-dimensional spectrum. All of those white lines are kind of different orders. They have different wavelengths associated to them. So what we do is we take this two-dimensional spectrum and kind of lay them all side by side to get a one-dimensional spectrum. And as we can see, this is what our one-dimensional spectrum looks like. So when I say that I study rainbows, this is what I'm doing almost all day, every day. I'm making plots like this, where on the y-axis, you have the flux or the amount of light that you're getting. And on the x-axis, you have wavelength, which is in unit of distance. And different elements will absorb different wavelengths of light. So each star has kind of this unique chemical fingerprint where if we look at the light that we get from a star, if we look at the spectrum and we see little dips in light, for example, we can see that there's hydrogen atoms here or calcium atoms here. We can see that all of these different elements have unique wavelengths, and you can start to build up this picture or chemical fingerprint of these unique stars. And so what I went and did was I found 29 different chemical abundances for this particular star. So that's ranging all the way from the lightest elements like lithium, and if you remember the periodic table, all the way down to really, really heavy elements like thorium. And so what I'm going to show and what I'm going to pose to you here as a question is, if we're looking at our star compared to its neighbors, where do they kind of lie in this chemical plane? So on these plots, I'm going to show you on these, there are these two different axes, X and Y. On the x-axis, you have the amount of iron in a star, which astronomers kind of use to proxy the total metallicity of a star. So the amount of iron on the x-axis. And here, for example, in this one, we have the amount of magnesium on the y-axis. And then in all of these plots, if we go back one, I'm going to show you our pink star, which is the star that we're looking at, Gaia BH3, compared to its neighbors. So this star was actually born associated with some other stars, and I'm showing the chemistry of those other stars in these kind of pink squares. So what I want to ask in all of these plots is, how close are those is that pink star to those pink squares? In the Born This Way camp, now remember, all of the neighbors would look very similar, but if our star maybe got some material donated by the supernova, then that star would look different chemically than its neighbors. So you would maybe see that this pink star looks far away from the other pink squares. But in the other camp, in the We Belong Together camp, in this dynamical capture scenario, we know that this star should look really similar to its neighbors because nothing kind of special happened to it chemically. It just got trapped in the gravity of this black hole. So we can actually go through and ask what's happening. You can ignore all of the other kind of points here, all of the other colors. That just shows kind of like different systems or galaxies. But if we're looking at this pink star compared to those pink squares, do they look close together? And I think in magnesium, I would say, yeah, they look pretty close together chemically. We can go through different elements like calcium, for example. I would say, again, that seems to match with strontium as well. Again, getting to those elements that you might not have heard of since maybe high school chemistry. It looks pretty similar. And all the way down to europium, which is one of the heaviest elements that we can measure. It's really, really hard when you get to these heavy elements to try to get measurements for these stars. So as you can see, there's only one other pink square here because there's only one other europium measurement. But we can see that it looks pretty close to kind of its other stars, to their other neighbors. So that's why I think, based on this star's chemistry, we're probably more in the camp of Mariah Carey, We Belong Together, because this star, our star, Guy BH3, looks really chemically similar to its neighbors.
Awesome.
Yeah, if we just, I think we can like summarize everything that we've heard of so far. Perfect. If we want to look at why this is weird specifically, we know a couple of different things. So one, this is an elusive type of black hole called an intermediate mass black hole. And we can find these weird black holes if we look for these binary systems. This is the lowest metallicity star to be found orbiting a black hole. And this can help us constrain early chemical formation and early black hole formation because we're really kind of looking back into time and using the star as a fossil. And when I say we don't really know how a system like this forms or survives, we think that it's likely this dynamical capture scenario. Even if we factor in the energetics of a supernova. When a supernova explosion goes off, you can imagine that there's a lot of energy just being dumped out, and that could disrupt an orbit. So maybe a companion would spiral in and eventually collide with the black hole or the thing at the center, or maybe it'd be kicked out of the orbit and it would no longer be in a binary system that we see today.
All right. Oh, that's so cool. Yeah. Even though already having already heard a bit of your talk, it's still always so cool hearing it again.
Thank you. Yeah, I love sharing this, and I love that people are interested in space and people want to hear about black holes and stars and the work that's being done at McDonald.
Yeah. Well, thank you so much for sharing your research and your knowledge. It's awesome having you on the stream.
Thank
For
you.
sharing it. Yeah. We'll have to close off a bit for the night. Some of you already saw the next slide, which showed a bit of a galaxy. We're gonna close off the stream with our final target of the night, which actually has an intermediate black hole in the center of it, a galaxy called Messier 74, known as the Phantom Galaxy. So here we have that view, that Messier 74, which is a large spiral galaxy, about 32 million light years away in the constellation of Pisces, and 85,300 light years across. So mention I felt it was a very fitting thing to end on since your research involved an intermediate-sized black hole, and this has an intermediate-sized black hole. Though this one was a bit too far away to kind of do with a binary, kind of using a binary systems, but this one was used with X-ray telescope. I felt a fitting thing to end on for the night, at least target-wise. Yeah. See, but this will be a good time to see if anyone in the chat has any questions to throw on in. So if any of y'all have any questions to give or ask, this will be the perfect time for y'all to ask. Like either for myself or Jay. Oh, yeah.
I was gonna say, while people are thinking of their questions, hi Judy, hi Rachel.
Yeah, hi y'all. So we're past friends and colleagues are in the chat. Yeah, question for myself or Jay or Zoe. You get to ask a real life astronomer. See if any questions come in. Let's see. Oh, I have a question for you, Zoe. Apart from your work on Gaia BH3, what's been some of your favorite other observing targets or or observing memories?
Yeah. I absolutely love McDonald Observatory. I love whenever I get to go out there. I think that my observing memories, I mean, you're up all night because the stars are up at night. So you just get kooky hours real fast. And that's when it's fun to have a friend with you, a co-observer, to kind of, yeah, just help you get through the night. But I think based on other sources or other objects, my kind of specific niche of astronomy isn't really involved with compact objects, to be honest. I kind of stumbled upon this. But what I love to do is to look at really metal poor stars. So, like I said, metal poor stars are probably older stars because they were formed at a time when there were only small amounts of metals in the universe. And I love not to be, my advisor calls himself the Indiana Jones of the galaxy. So I guess I can't claim that in terms of being a galactic archaeologist. But I really love looking at these old kind of fossils of the Milky Way to try to understand how the Milky Way formed and specifically how kind of the early building blocks of the Milky Way formed. So any star that's old, metal poor, send it my way. I want to look at it.
Right, awesome. Thank you. Oh, we have some questions. One from Judy. Zoe, when will you be back at McDonald to observe, or are you finished?
That's a great question. And as of a couple hours ago, I found a really possibly interesting source that I would love to follow up that has kind of to do with these elusive type of black hole star binaries. That would be observed with HET because it's a really faint star, so we need a much bigger telescope, and the HET is like a 10-meter class telescope compared to a 2.7-meter. And as you guys know, the HET is through remote observing. So I'm gonna have to figure out a proposal of a cool star to get me back out there physically.
Nice. Oh, another question from Paul Devo S2J on YouTube. Are the metallicity of the stars near the BH3 similar to it as well?
That's a great question, and the exact kind of question that we want to be asking. Yes, they have very similar metallicities, and again, that's because they were born together. So it makes sense. It tracks with kind of our idea of dynamical capture that these stars are all related, especially chemically, because the metallicity and the other chemical abundances of this star is really close to its neighbors.
Thank you. Some other little things, just kind of since we are talking about black holes, just I think will be a cool thing. Just mention some cool facts about black holes. As I said earlier, we don't know much about black holes, but some of the cool things we do know, as kind of let Jay mention one of their favorite words. What happens if you get really near a black hole, Jay, or fall into a black hole?
One of the theories is that the sense of gravity is just so immense that basically your body will get stretched out to where it kind of resembles, back to that pasta, the thing of spaghetti. So it's called spaghettification, which is an actual term in astronomy, which is so cool.
Yeah. Other thing about black holes, the gravity becomes so intense and have to be going faster than the speed of light to escape the black hole. And also with black holes, as you're going in, kind of time gets really weird. Your perception of time will be very slowed as you're going closer to the black hole. And they're kind of more frequent than we expected. Kind of as Zoe mentioned, just with the ways we can detect the black hole, they're they're also like smaller than some thought. When we first thought about black holes, we thought they were just a theoretical thing, like, hey, black holes are a thing. Then like they're more of a thing than we thought. And now we're learning more and more about them. And they're just such a cool subject that we're still learning more about. Let's see. Another question from YouTube was the nearest star to our binary system. I'm assuming that means what's the nearest star to us. If that is, that will be Proxima Centauri, which is about 4 light years away.
Yeah, and Proxima and Alpha Centauri are actually a binary system themselves. So that is the closest binary to us.
Let's see. Don't see any other questions that have come in, but that's about all the time we have for today. Thank y'all so much for joining in. Oh, question from Instagram. Oh, and that's actually from Joshua Santana. What other sources, instruments, telescopes do you use for research, Zoe?
Hey Josh, great question. So I love, like I said, the 2.7 meter telescope, specifically the Tolkude spectrograph, is kind of my bread and butter. But for kind of the other side of research that I'm doing, I've been kind of in this data driven phase. So I'm using, instead of just looking at one star for a really long time, I'm looking at hundreds of thousands, if not millions of stars at one time and doing kind of like statistics on those stars. So those stars are coming from telescopes like Gaia, or missions like Apogee run through SDSS, which is what was started on the APO telescope. Let's see what other sources. I use right now. I'm working on specifically HETEX stars. So if you've heard of McDonald, you've probably heard of HETEX. It's the Hobby Eberly Telescope Dark Energy Experiment, and it's an experiment run on HET to kind of characterize how dark energy moves, what dark energy is. Don't ask me any questions about that because I have no clue. But throughout kind of this quest to understand dark energy, HET has observed a lot and has accidentally observed a lot of stars. And so, kind of the dark energy people's trash is my treasure. So, I take all the stars and I look at these stars and try to understand kind of like the bulk properties of these stars and how they move in our galaxy to again piece together how the Milky Way formed.
Awesome. Well, that's about all the time we have for today. Thank you so much for joining us, Zoe. And thank everyone for joining on tonight's live stream. Again, if you're just joining in or want to just join in late or just want to re-watch the stream, this stream is staying up on our YouTube channel, McDonald Observatory on YouTube. If you want to share this with other people, please do. Feel free to watch as many times as you want and share it to other people so they can learn more about astronomy and black holes and white dwarfs, or just all the cool space stuff. And do follow our social media pages, McDonald Observatory on YouTube and Facebook and Instagram. Also, do like and subscribe and share and all that good social media lingo and stuff. Also, the visitor center is open to the public, so you can come and visit us. We do have public programs about the sun, so you can learn more about the sun. Visit our research telescopes. We do guided tours for that, and star party programs. So you look through the smaller telescopes and maybe not be able to see black holes and the neutron stars, but you can see at least the remnants of some of these, like a planetary nebulae. Like planetary nebulae is something we do try to show during our programs if we are able to, because the moon does get in the way of being able to see those at times. But we do still show some really cool objects. Reservations are recommended, especially during holiday times, because we do fill up fast. But do come and visit us. And do check out our live streams as well, because we have talked about lots of other cool subjects like galaxies, novae, nebulous, stellar evolution, lots of other cool stuff. And yeah, we really hope y'all enjoyed the program. And that y'all have a good night and happy holidays. Take care, everyone. Good
Bye,
night.
everyone.